So welcome to part two of the Mathematics for Machine Learning series. This will be on scalars, vectors, matrices, and tensors. So this hits the linear algebra portion of our program and some relationship with how that lines up with Python and how Python handles the linear algebra. We'll talk some about that. There's more behind that than we can get into in this series. Just want to get basic definitions down. Scalar is basically going to be treated as a number. It can be a little more complicated than that, but here, for the most part, we're going to be dealing with scalars that are integers, which means whole numbers, or floating point decimals, floats in computer science, decimals, real numbers in mathematics. It can be a little broader than that in mathematics, but we're going to stick with this just as think of it as a number, mostly integer or decimal. So vector, you might have seen this in physics. For example, a vector often represents a force or an acceleration or velocity. It's an amount with a direction on it. We're not going to think of it really in that way. We're going to think of it as a list of scalars, a list of numbers, or an array, one-dimensional array. And typically in mathematics, we write those vertically. So if we were going to look at, say, the RGB values of a pixel in an image, we might end up with 250, 108, 63 if the range was 0 to 255. And that would be fairly red, a little bit of green, some green, and a little bit of blue. That you could have one pixels color intensities represented that way. A matrix is going to be a two-dimensional array of numbers. This could be a variety of things. For example, any record in the digits data set would qualify as a matrix. And so that would have 8 rows, 8 columns. Each entry is a number from 0 to 15 that gives you the darkness or brightness of that pixel in grayscale and gives you a picture of a handwritten digit. A tensor is a 3+ dimensional array. If you come across the term tensor in mathematics or physics, they're probably going to mean something quite different than that. But in machine learning, it's very clearly just a multi-dimensional array. If you look at all of these, you can actually include all of the previous ones in any of them. If you have a vector that has length 1, it's the same thing as a scalar. If you have a matrix where one of the two dimensions has a size of 1, then you have a vector. So you can think of this vector that I have here as a 3x1 matrix. A tensor, if 2 or more of the dimensions are 1, you can think of this vector again as a 3x1x1 tensor. Every one of these includes the previous ones. So a tensor can really be thought of as much as it's just a multi-dimensional array. But we'll typically stick with it this way. Scalar is going to just be the number. The vector is going to be one-dimensional. Usually it will have more than one entry in it. Pretty much always. A matrix, again, usually will have both dimensions will be at least 2. And often many more than that. And then tensors, again, each dimension will be at least 2 typically. Otherwise, we would just call it a matrix or a vector or a scalar. In Python is going to see a vector, for example, as a list. And you can do a matrix as a list of lists. And then a tensor could be a list of matrices and so on and so forth, list of lists. In NumPy, you've got the NumPy array constructor. You can use a D type on that, which is going to be a data type for it. For example, you could do int 8, which would be an 8-bit integer. You can do uint8, which would be an unsigned 8-bit integer. So int 8 would be from -128 to 127. Uint8 would be from 0 to 255. You can do float 32, which would be a 32-bit floating point decimal. Whatever it is that you want to put as your data type, the NumPy will take that and assume that each coordinate fits into that category and treat it as that way. So it's a little different from the way we often do things in Python, where Python dynamically types everything for you. When you do vector or matrix in Python, where everything's dynamic, if you do it without NumPy, it will dynamically type it for you. The advantage to doing it with NumPy is that you are going to have a significant improvement in efficiency of calculation, and you're going to have a significant improvement of efficiency of memory usage. For example, you set a variable equal to a number. If you set if you have a list with a whole bunch of things, like you can put anything in a list, right? And it takes it. You can put a number in the first, a string in the second, a list in the third, a dictionary in the fourth, entry in the list, whatever. You can put whatever the heck you want in the list. The reason Python can do that is because every element of the list is treated as an object. And so really it's a list of memory addresses, and you just link to whatever memory address the information is stored in, and it doesn't matter where that is or how big it is because it's just a memory address. NumPy very specifically allocates, if you have, for example, a NumPy array that's 1024 by 768 by 3. That's a tensor. There will be a 1024 by 768 image with a color depth of 3, say RGB or BGR, and you say it's all in uint 8, then it's going to assign 8 bits for every one of those entries. So you would get 24 bits times 1024 times 768 memory locations, 8-bit 1 byte memory locations reserved for this array, and it will fill them. The advantage there is that you've allocated exactly the same amount of memory as you need and only as much as you need, and you're not over allocating memory. So with a vector, with a matrix in Python without NumPy, you're making this long list of lists, and each one of the lists is actually a list of memory addresses of objects and so on and so forth. And so the magnitude of the memory usage goes up and up and up. And once the magnitude of the memory addresses go up, memory usage goes up and up and up, you're using more processing power because you have to follow this path to get to each of the numbers. And if you're following a path to get to each of the numbers as part of your computational process, then your computational process is going to take a heck of a lot longer because you have to sort of dig out each one instead of just knowing that it's going to be, so many entries along a string, and a string of memory addresses, and you know exactly which one it's at, and you just read that byte and you're all set. It's much more efficient to use NumPy when you can, and that's going to make a big difference. It's a big deal in machine learning. When we get further into this and we start to play with possibly using GPUs, which stands for graphic processing unit, they're also TPUs, tensor processing units. These are processors that are specifically designed for doing large array calculations and are much more efficient for doing array calculations and therefore much more efficient for doing machine learning calculations. The stuff we're doing now, the early on machine learning processes are quite efficient, and you can still run and build these models in a matter of milliseconds or maybe a few seconds. It won't make a spectacular difference whether we're using a GPU or a CPU at this point. A regular old laptop CPU will do just fine with all the scikit-learn algorithms. When we get further into this and start building neural networks, we'll have a little bit more interesting time of that. And we may have to do some upgrading of and move your work onto computers that have graphic processing units and things like that so that we can make the calculations a lot more efficient. So if I have two vectors, I know I just want to add them. We've done this a little bit with the OpenCV in particular, where we added pixels across two images to combine two images. For example, if I just have, let's say, so you just add coordinate-wise, and I'll write out the intermediate step to make things a little clearer here. So very straightforward, you just add, if you want to add two vectors, you add the first coordinates and put that in the first coordinate, add the second coordinates, put that in the second coordinate, and then add the third coordinates, put that in the third coordinate. So 128 plus 27 is 155, 207, and 140. You can also multiply a vector by a scalar. It literally is scaling the vector. So if I have, and I want to multiply this by 5, then I'm just going to multiply each coordinate by 5. You multiply coordinate-wise. So I get 52, 10, and 65 in this case. So this is important for brightening or darkening an image. So for example, if you have an image and you have all the RGB values, you can multiply by, say 1.5, and it'll make it 50% brighter. You just have to make sure that you don't wrap around, and you have to worry about what happens if you get up to 255, that, just do an if statement. If it's greater than 255, reduce it to 255 so that you don't wrap around and actually make it darker. And then you can brighten an image that way by hand using OpenCV. So dot product of two vectors, I'm going to take a little bit of a different tack to this. I'm going to look at it. So for example, if I have 5, 3, and I take the dot product of that with -2, 4, one of the interesting things about a dot product of two vectors is you don't get a vector out of this. The dot product of two vectors yields a number, and it doesn't matter how many coordinates are in the vector, that's still true. You're going to have a result of just one number. I multiply the first coordinates of the two vectors, add on what I get when I multiply the second coordinates of the two vectors, and so on. And so in this case, I'll get -10 plus 2 plus 12 is equal to 2. Geometrically, I'll take a look at this because this will come up. So if I have the vector 5, 3, we're here. That means I start at the origin and I come out to the point 5, 3, and then -2, 4. I go left 2 and up 4 to the point -2, 4. And when I take the dot product of these two, what I'm actually looking at is I've got some measurement of this angle between these two. So if I want to look at this geometrically, I get cosine of the angle between them is equal to the dot product divided by the length of u times the length of v. The length of u is going to be, and we'll talk more about this, this is sort of a ball of wax in some ways, but the straightforward answer to this is if I call this u and this v, then the length of u is just square root of 5 squared plus 3 squared. You're just going to do Pythagorean theorem. Go over 5 up 3. Well, what's the length of that hypotenuse? That's going to be 34. And then the length of v here is square root of 4 plus 16, because it's negative 2 squared and 4 squared. So you get 20, square root of 34 times square root of 20. This is close to 6. This is about 4.5. And so we should be at about 27. So this is somewhere around 2 divided by, I don't know, 25, 27. And so we're looking at about 0.08 or so. And so this cosine is very small. If cosine is close to 0, in this case positive, then this angle should be a little less than 90 degrees. And if we look at this picture, I know my picture is a little rough, but this looks a little less than 90 degrees. So that matches with the intuition. So the dot product gives us this geometric interpretation that's very useful. The main goal of taking a dot product of two vectors is to calculate the angle between those two vectors. That's usually what it's used for. Even if it's not directly used for that, usually the angle between them is hiding somewhere in that interpretation. Matrix arithmetic, this is not exciting or surprising. I'll just take a nice easy example here. You're just going to add coordinate-wise. 5 and negative 2 is 3. 3 and 3 is 6. Negative 4 and 4 is 0. Negative 1 and negative 2 is negative 3. And so you're just adding coordinate-wise. If I want to multiply a matrix by a scalar, same deal as it was with a vector. I just multiply each coordinate by that amount. Something to point out here, this is true of vectors as well, and I breezed by it in vectors, but it's true of matrices, true of vectors. If you want to add two vectors, if you want to add two matrices, they have to be the same size. That is an absolute requirement here, that you can't add matrices of the same size, or that are not the same size. They must be the same size. And I know a couple of you ran into this in your OpenCV projects. You're trying to combine two images and place one image onto another, and you're trying to do a matrix addition in order to pull that off. The two matrices have to be the same size in order to do it. And so what you do if that happens where you don't have the same size is you'll take the matrix that you have and you'll embed it in a larger matrix of zeros so that the two match. And so, you know, if the one is bigger than the other in both length and width, then you just take the smaller one and make a new matrix that's all zeros, put the matrix you have that's smaller, embed it in there in the right place, and then add the two directly that way, because then you're just adding 0 on all the coordinates that are not the ones you're interested in. And that's easy in Python. In NumPy, there's an np.zeros that makes a matrix of a certain size that's full of nothing but zeros, and then you can put in your image where it is that you want it. Same deal with vectors. Vectors have to have the same length in order for you to add them. If you want to multiply a matrix by a vector, so here I'll do a little bit of a geometric example. So I'll take this matrix. So to calculate the product of this matrix times this vector, I'm going to use the dot product of the first row of this matrix by the first column, the column of this vector, in order to get the first entry of my result. So I'm going to have 0.866 times 3 plus 0.5 times 1. And then on the other one, I'm going to have negative 0.5 times 3 plus 0.866 times 1, because we'll take the second row times the first times the column in order to get the second entry. So here, when you do all that calculation, do the arithmetic, we end up with roughly 3.1 in the x-coordinate and negative 0.6. We can interpret that geometrically, and we do. If I plot the original vector and then the resulting vector, you can see that the result of multiplying by this matrix is clockwise rotation of 30 degrees. I constructed this matrix using sines and cosines of 30 degrees in order to create that. There's also a functional interpretation of this. If I have a linear function where, in this case, I have two input variables and two output variables. So if my two input variables are x and y, and my output is I take the x coordinate and multiply by 0.866, add that to 0.5 times the y coordinate, then that is the first coordinate of my output. My second coordinate of the output is negative 0.5 times the x plus 0.866 times the y. If I look at that as a function, that has the same exact effect, the same output as if I multiply by this matrix. and then I had the vector xy here, then I would get exactly, these two things would be exactly the same. And so every matrix that you multiply by is the same, has the same effect as applying a linear function, and every linear function in the right number of variables can be represented as a matrix with the right number of rows and columns. And so there's a correspondence between matrices and functions, and every matrix can represent a function. Every function can be represented by a matrix. And so this correspondence is a huge part of linear algebra. It's called linear transformations, and is something we do all the time in linear algebra. But this idea is important for transforming our data sets, our work into other coordinate systems and things like that. If you want to multiply two matrices, I'll do a non-square example just so you can see it. So if we have matrix multiplication, this is a 2 by 3 matrix. This is a 3 by 2 matrix. When you want to, if you want to see if two matrices can even be multiplied, the thing to look at is the middle of those two numbers. So the number of columns of the first matrix has to match the number of rows of the second matrix. Those two have to match. And then the result is going to be the other two dimensions. And so we are going to get a 2 by 2 matrix as a result of this product. So if they're both square matrices, they have to be the same size. If they're rectangular, the columns in the first have to match the rows in the second, and then you get a result which is the rows of the first by the columns of the second. And the reason for that is that what we're going to do here is the same idea as when we did matrix times vector. We're just going to do it many more times. We're going to do dot products. And so my first dot product here is going to be the first row by the first of the first matrix by the first column of the second matrix. And so I'm going to get 6 times 3 is 18, plus 5 times -3 is -15, and then plus 2 times -1 or -2. And then the next entry, if I go over one, I'm going to go over one column because I'm moving over one column in the result. I'm going to move over one column in the second matrix and do first row by the second column. I put that entry in the first row, second column of the result. So I get 3 times 2 is 6, 5 times -2 is -10, and 2 times 7 is 14. And then we do the dot product of the second row, first column. I put that result in the second row, first column of the result. 6 times 4 is 24. 1 times -3 is -3. 3 times -1 is also -3. And then the last entry will be the second row, second column. So I get 8 -2 plus 21. And so in the end, my product is 18 minus 17 is 1. 20 minus 10 is 10. 24 minus 6 is 18. 29 minus 2 is 27. And so you see how we get the 2 by 2 as the result. So notice if you had two square matrices, you could just do the obvious thing and multiply coordinate by coordinate, just like we did when we added. That's not wrong to do. It's just not useful to do the way this matrix product is useful. So this matrix product is much more useful because what it represents in terms of functions. So if I've represented both two linear functions as matrices that I'm multiplying by vectors to evaluate them as functions, then when I multiply two matrices, then I'm doing the same thing as if I'm composing two functions. The matrix multiplication here matches the function composition. And so I'm really composing these two linear transformations into a single linear transformation. So if I were going to look at these two matrices as functions, this first one, because it's two columns, as 3 rows and 2 columns, it would be multiplied by a 2-dimensional vector because the number of columns here has to match the number of entries in the vector. So this is as a function would take in a 2-dimensional vector and output a 3-dimensional vector. This one would input the second one would input a 3-dimensional vector and output a 2-dimensional vector. And so as a function composition that takes in a 2-dimensional vector, outputs a 2-dimensional vector, and that matches the function that this matrix represents as a linear function. The long and short of it is that if you want this correspondence between matrices and functions to continue to line up through function composition and matrix multiplication, you have to do matrix multiplication this way, and then the two match. And so this is a much more useful representation of matrix multiplication, and so we use this one. So just to be aware, if you use NumPy and you have two NumPy arrays and you just multiply them here, if you just had, if these were both NumPy arrays, this is coordinate-wise not so useful multiplication. If you want to carry out the real matrix multiplication, you really want to use the matmul, M-A-T-M-U-L, matrix multiplication function within NumPy in order to carry out your matrix multiplication. One warning here is that m times n, using the useful matrix multiplication, is not necessarily equal to n times m. We're really used to the idea that 3 times 2 is the same thing as 2 times 3. It's a really nice thing. It's really useful. Matrix multiplication does not work that way. Just as function composition, if you remember from your high school courses, function composition is not commutative. You can't switch the order of two functions in composition and get the same result. You get two different results. Same deal here. Because matrix multiplication is representative of function composition, same deal. If you switch the order, you get a different result. And so you have to be really aware that a matrix multiplication is not commutative. The order matters. So if I apply this matmul mn, and that's not necessarily going to give me the same result as matmul nm. It's pretty rare that it does. Really be painfully aware of that. It's an easy thing to get tripped up on. You wouldn't be the only one. First one, last one. Werner Heisenberg is famous for the Heisenberg uncertainty principle in physics. Made that mistake at one point, and it held him up for quite a while in his research because he didn't realize what the mistake he made was. He didn't realize the objects he was looking at were actually representable by matrices, and therefore their combination should be non-commutative. And so he was having a real struggle with this, and eventually realized that if he represented these things by matrices, then it all made sense. And part of that is because of the non-commutativity of the multiplication and combination. You should be aware of a couple of quick data transformations. Reshape, you've used this in NumPy. It shows up in a lot of the the scikit-learn library examples, where you just have to reshape a matrix so that it works better with the function you're trying to use. And so, for example, with the digits data set, each record is 8 by 8, but we want to transform it to 64 entry vector. It's a very common process to go through because you want to just put them straight across, and it'll just put them in sequence. So it'll go across the first row. So the first 8 coordinates are the first 8, the top row, the next 8 coordinates in your vector are the next second row, the next 8 coordinates are the third row, and so on. And so it's very common to want to reshape your data and either, make, if your record consists of a matrix, to convert it to a vector. So typically you just want the record to each consist of a vector. Transpose is you're going to switch rows and columns, and this is really useful. So for example, if you want to compute the maximum value that a variable takes on, or if you want to compute the average value of a variable, then you transpose it, and then your rows, your lists, each list within your array, each subarray within your array becomes the variable instead of the record. And so you can calculate, run calculations on your variables that way. Once you take the transpose, if I have my data is some NumPy array, and then I have tr is NumPy transpose of my data, then tr0 is the same thing as my 0th variable, all the different values of the different records as a list, or really as an array. And so that's a really useful, a really useful operation to be able to just flip the data array so that then you have your arrays as sublists, subarrays, and then you can just go ahead and do the calculations on those subarrays and get the min, max, average, standard deviation, whatever you need for each variable one at a time.